today we are going to study inverse of a relation first. This is the beginning we start with, right? Inverse of a relation. Inverse of a relation. Now, what is inverse of a relation? Just you see. If suppose we have a relation already, R order pair AB, right? Here, this A belongs to A, B belongs to B, two sets are there, R is a relation, and there is a condition, right? So that condition already you have seen in example. There will be a condition relating A and B. B, any relation on A to B. Then R inverse. R inverse will be simply what? It is the ordered pair B, comma A, where A, comma B is belonging to R. That means once if you define R, then you can define R inverse is called the inverse of the given relation. Right? Right? And this relation is from, and this relation is on B to A. Right? So this is the idea of inverse of a relation. What I got, right? Now we'll be taking examples, right? So that it will be clear to you. Say a relation. First, I'll take a relation in the ordered pair. Suppose I have given you a relation like this. Suppose this is the given relation. Then what will be the inverse of this? Simply ordered pairs will be reversed. Because whatever was the domain for the original relation, that becomes the range for the inverse. And whatever was the range for the original relation, that becomes the domain of the inverse relation. That's the idea here, right? This is one of the example. Now, one more example I would like to take, where we'll be giving conditions. Say, I'd like to take this relation where B is equal to A plus 1, right? A is taken from set A, B is taken from set A, right? Where A is the set 1, 2, 3, 4, say up to 10, right? Now we have to find this. So what I do, again, I'm telling you that we'll do in a short way first. We'll draw the diagrammatical way, and then we will try to convert this into theoretical, right? That is analytical one. So these are the two sets. Two sets means both the sets are same here, only they are both A. So this is the set A, and this is the set E again. So from A to A, we are going to relate elements. We are going to get elements relation between this. This is the relation R. Right? What are the elements in A? It is 1, 2, 3, 4, 5 up to 10. Right? So we'll be writing those elements here now, and then we'll try to see. Here, let me put the elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are the elements in the set A. Similarly, let me write the elements here also. So these are the elements in the right side set. Now, just think about the relation and try to correlate the elements, right? So first of all, you try to see what is the relation link. B should be one more than A. That means whatever A you select, it is related to one element B, which is one more than that. That means one will be related to 2. Like this will be related. So I can draw the figure from here. This will be related to 2, right? Then here this 2 will be related this 2 will be related to 3, then this 3 will be related to 4, right? In that way, you can go for relating all this. This 4 will be related to 5, okay. 9 will be related to 10, 7 will be related to 8, right? 5 will be related to 6, 8 will be related to 9, then this 6 will be related to 7. So you see, here I have just taken a very simple relation, and then you can easily identify that which element is related to what. One is related to two, like this, right? So now once you try to write this whole thing in the roster method, then what I should write here? It is 1 comma 2, 2 comma 3, 3 comma 4, 4 comma 5, 5 comma 6, 6 comma 7, 7 comma 8, 8 comma 9, and then 9 comma 10, not more than that. So immediately our inverse will be what? You just reverse the order pairs. That's all. So this is the inverse. So inverse here is not a difficult task to do, right? So please keep on noting down this, and once you've finished, you indicate me. So this is the inverse. Once you've finished, please indicate me. I'll go for the next. Okay. So after doing the inverse, we are going to a very important part. That is the types of relations. Types of relations, right? Actually, these are the parts from class 12. So I'm mixing both the chapters, right? Because they are the continuation. So we'll be just together finishing it so that it will not create a problem. So now the first type of relation we get is reflexive relation. Now, what is reflexive relation? I'll be giving the definition and then I'll take examples to show you. A relation are defined on A. If I write defined on A, it means it is from A to A, such that for every element A of capital A comma A belongs to R. Right? That means A is related to itself. If this type of relation you get, that is called a reflexive relation. Now we'll be taking examples, a lot of examples, so that it will not be creating any problem for us in understanding this. Example number 1. Let A set of all straight lines in a plane, right? This plane is given. Right? One plane is there in plane. Whatever possible straight lines are there, we have taken, and we would like to define a relation. The relation is defined like this: L1 comma L2. They are said to be related if L1 is parallel to L2, meaning L1 L2 if they are parallel, which are taken from the given plane given set A, and if they are parallel, we say that they are related. So this is the relation we have. Now here you see, we'll just try to justify whether it is reflexive or not. So you can write for every line L belongs to A, we can say that L is parallel to L. Okay, there is now a question because we did not get this. Actually, now onwards, parallel definition is not that they are not intersecting if you extend them in both the directions. This was the definition we use in lower classes. Now, what we will say, two lines are parallel if the angle between them is 0 degree or 180 degree. So, if I draw like this one line two times, right, or coincident line, what is the angle between them? 0 degree. So, it means one line is parallel to itself. So that way we can write this. And if it is parallel, what I can say, L comma L belongs to R. And this is happening true for all L belongs to A. Therefore, what I can say, R is reflexive. If this doesn't happen for everyone, then we say that it will not be reflexive. But I have taken an example of reflexivity. Right? Now one more example we'll take. Let A set of all triangles in a given plane. Set of all triangles in a given plane. And the relation we would like to consider is that two triangles, triangle 1, triangle 2 are related if triangle 1 is congruent to triangle 2. And this triangle 1 and triangle 2 are taken from the set A. So from here also you can easily justify that these are, this will show you a relation which is reflexive. Why? For any triangle belonging to A, can we say that the triangle itself is congruent to it? Yes, we can say every triangle is congruent to itself, because congruence means what? Equal in all aspects. So obviously one triangle is equal to itself in all aspects. So from here I can say that this belongs to R. So this will imply that R is reflexive. Some examples I am taking, right? Okay, let me just try to tell you that I'll change the name here, because afterwards I'll refer to it, right? Let me make it R1. This is R2. You also make change, because when I take these examples, I'll again say that R1. Matlab, you have to see this relation again. Once you finish, please let me know. I'll take few more examples of reflexive relation, so I have to go in detail. Okay, thank you. So we'll go for this. Some examples I'll take where it is not reflexive also. Okay. Now number C. Example number C. So let A, I want to consider here, say natural number, set of natural numbers. Set of natural number I want to consider, and R. R is what? Say A and B will be related. A and B will be related if A is less than or equal to B. A is less than or equal to B, where A and B are taken from A. Is this relation reflexive? So you just say for A belongs to capital A, that is natural number. Can we say that this happens? Yes, we can say A is less than or equal to. Had it been strictly less than, we could have not said, but here it is. So from here I can say that A comma A will be related and it will be in R. Okay, let me make it R3, in R3. So I say that R3 is reflexive. Right? R3 is reflexive. Right? Whereas I write just here it as a C dash by the side. Had this relation be something like this, say dash I'm writing here, A, B, A is strictly less than B, A, B belongs to A, then it would be not reflexive. Why? Simple reason, because A cannot be less than A. This is not valid. Not valid. So this relation would have not been reflexive. Be careful. Only the equality is a matter here. Right? That's a big matter in fact. We sometimes may overlook. Number D, would like to consider this. A very important relation I'm going to consider. A is a set of integer. and suppose R4 is the result. A and B are related. If A, this triple sign that is congruent बोलते हैं इसको, we'll explain you. Congruent modulo 3, where this A comma B belongs to Z. Now, what is the meaning of congruent modulo? I'm just trying to tell you in the outside explanation so that you understand. Actually, it is a simple concept. If A congruent to B mod 3 I write, it means A minus B is divisible by 3. That means if A and B, if the difference is divisible by 3, then we say that A is congruent to B mod 3. That is how we read. So here if I take example, if I write 2 and 5, right, or I can say 2 and 5 belongs to R4 of course. Instead of that I can write 2 is congruent to 5 mod of 3. Check it. Why it is? Because 2 minus 3 will be minus 3. That is divisible by 3. So that way we can define the modulo. So in this case, we can have this as reflexive. Why? For A belongs to capital A, yeah, that is Z. What do you say? A minus A is equal to 0. Is it divisible by 3? Obviously, 0 is divisible by every number, so it is divisible by 3. Therefore, if it is divisible by 3, I can write that A is congruent to A modulo 3. That means A comma A belongs to R4. Right? So this is reflexive. Therefore, R4 is reflexive. Please remember all this because we are going to come back to this. Right. So this, for example, one more example I'll take and then I'll go for the next step of relations. Once you finish, please let me know. Okay, so we'll go for the next part. So here, example number E. Say A is the set of all straight lines in a plane, in a given plane rather, right? All straight lines in a given plane. And R5, I'd like to discuss like this. L1 and L2 will be related if L1 is perpendicular to L2, where L1, L2 are belonging to the set A. Clearly, we can write clearly for L belongs to not L1. Clearly, for L belongs to A, can I say that this is perpendicular to this? Very clearly, you can say that no, it is not perpendicular. Right? If it is not perpendicular, that means that L comma L does not belong to R5. Therefore, R5 is not reflexive. So we have got 5 examples. Please remember this all 5 examples because we are going to come back to these examples. Once you finish, please let me know. Okay, now we'll be going for the type number 2, that is symmetric relation. Symmetric relation. Reflexive then symmetric. So you write a relation R on a set A is said to be symmetric. Symmetric if for every AB belonging to A A comma B belongs to R implies B comma A belongs to R. That means whenever for 2AB, A comma B is in R, that is A is related to B, then we should be able to like give comment on B is related to A or not. If it is related, then we would say that this is symmetric, otherwise not. So now I'll not rewrite the relations. I'll go back to the relations examples. One you can see we have talked about the parallelism R1, right? R1 is symmetric, right? As directly I'm doing. See, you can consider L1 related to L2 in R1. That means they are related if the lines are parallel. Okay, if two lines are parallel, I can talk them in any order. I can write L2 parallel to L1 also. Once I get L2 parallel L1, I can say L2 comma L1 belongs to R1. Therefore, R1 is symmetric. R1 is symmetric. Please see that. R1 is symmetric. And once you finish, we will explain. We'll go for the next. Okay. So I'll not change the page. I'll do it here only. Just see. Now we'll come to the example B, where we have considered R2. R2, if you see, it is the congruence relation, right? So R2 is also symmetric as triangle 1, triangle 2 belongs to R2, means triangle 1 is congruent to triangle 2. That obviously implies that triangle 2 is congruent to triangle 1. That will tell you triangle 2 and triangle 1 is in R2. Right, and this happens true for all triangle 1 and triangle 2 take from A. Therefore, R2 is symmetric, right? So we got the relation. Once you finish, can you please tell me immediately? Okay. So now we'll be discussing the remaining two. C. In C, we have talked about the natural number and we consider the relation as less than or equal, right? So R3 is not symmetric. R3 is not symmetric, right? R3 is not symmetric. As if you consider A, B belongs to R3, that will imply A less than or equal to B. But it will not imply B less than or equal to B. Now you may be saying, sir, A equal to B here, so यहाँ पे भी तो B equal to A. Okay, that is only one option. What if it is A strictly less than B? Then that option will not be there. So it is not like this. So this implies C. Here I do not want to write the implies here, then it may be confusion. So here I'll write implies. So I should write B comma A belongs to R3. Now are you confused? Actually, if I keep this left part hidden, this till here, so this part implies this much. So in between the non-implication is indicated there. So ultimately what you arrived at, ultimately you started with AB in R3, but you did not get BA in R3. Therefore, R3 is not symmetric. Anyway, that conclusion already I have written at the top only. But okay, fine. This is the explanation. Now next, in D, we have the congruency. It is symmetric. So let us not give the comment at the beginning. Let us prove it first, right? Then see how we'll be getting the result. For A comma B belongs to A, suppose, we have considered this belongs to R4. That tells you that A congruent to B mod 3. That means, what does it mean? A minus B is divisible by 3. That means 3 divides A minus B. This is the symbol. Okay, if 3 divides A minus B, obviously 3 will divide negative of that number also. It's a common sense. If a number divides a given number, negative of that given number can be also divisible. Right? So if you now simplify, it will become B minus. That means I can say B is congruent to A mod of 3. So that means overall में क्या imply करेंगे हम लोग? Here B comma A belongs to R4. That is, I am writing here, A comma B belongs to R4 necessarily imply B comma A belongs to R4. And this happens true for all ABs satisfying this. So R4 is symmetric. R4 is symmetric. Please note it down. And then last one is about the perpendicularity. So this will be symmetric. So I can write also like this: for L1 comma L2 belongs to R5, we get, what do we get? L1 perpendicular to L2. Obviously L2 will be perpendicular to L1. So L2 comma L1 will belong to R4. Therefore, what did you observe? L1, L2 started with R4. You have finished with L2, L1 belonging to R4, right? And this is for all L1, L2 belongs to.
R5, right?
It was R5, 5, 5. Thank you. Thank you for the correction. R5. Thank you for the correction. It is R5. So it is here. Therefore, R5 is symmetric here. See, it was not reflexive, but it is symmetric here. So I got all these 5 examples discussed. Once you finish, please indicate me. Okay, so now I'll be going for the type 3, right? Type 3 relation. Number 3, that is transitive. Transitive relation. Transitive relation. Just a minute, this let me correct. It is RELA. Transitive relation. TRANSITIVE. Transitive relation. So a relation R on A is called transitive if AB belongs to R and BC belongs to R, implies AC belongs to R for all ABC in A. If this happens, we call it transitive. Please note it down, then I'll explain it to you. A and B are related. B and C are related. See, wherever the first relation finishes, that is the image of the first product pair, should be the starting element, that is pre-image, right, in the second order pair. So in that case, I should be able to relate A and C. If this happens, then we say that the relations are transitive, right? So if this doesn't happen, we will say that it is not transitive. So this is the very important case. Now, before I go for any example of this, any examples means already we have. Just I would like to discuss something here separately. Very important, right? First, I'll write it, then we'll be getting the examples also. Okay, what if this happens? That A and B belongs to R and BC belongs to R, but A and C does not belong to R. Means AC belongs to R is not implied by this. Then what will be our conclusion? The relation is not transitive. Be very clear about it. This is not transitive. Right? This is what the conclusion we can have. Very nice. But what if my condition is something like that I try to find AB and it is found in R, then I try to look for BC, but this doesn't belong to R. Then what we will say? This condition also might come. I'll discuss this example also. This might also come. There is a difference. Here A and B, these two are both there, but third pair is not there, so non-transitive. You have the counter example. But here you do not have any counter example to say because you cannot arrive at A comma C. Right? A comma C will be there or not. It is not going up to that point only. Before only you have finished. You have finished in the sense that you are unable to find this order pair. So if you face this kind of situation, it will say that the relation is transitive. What it is? Trivial. It is transitive trivial, yeah, trivial transitive. Trivial means you do not have any now statement to say that the relation is not transitive. You do not have counter example. So when you face a situation where you do not have counter example to say that it is not like this, so unfortunately you have to accept it to be transitive, and that is called trivial transitive. So this is the thing you have to remember. Now I'll be discussing the examples what already we have included. I'm talking about R1, right? R1 is transitive, right? R1 is transitive. As we have to consider two lines like this in R1, then L2 parallel to L3 in R1, then that will imply what? L1 parallel to L2, L2 parallel to L3. And now a very simple geometry idea you can use. L1 parallel to L3. That obviously will imply that L1, L3 are related. Therefore, you have satisfied the condition of transitivity. So R1 is transitive. R1 is transitive. B. Talking about R2. Talking about R2. In R2, we considered triangles. Here also it will be true, right? It is also transitive. As triangle 1, triangle 2 belongs to R2. Triangle 2, triangle 3 belongs to R2 implies that triangle 1 is congruent to triangle 2 and triangle 2 is congruent to triangle 3. It means all the three triangles are equal in all aspects. So in particular triangle 1 and triangle 3. So that will tell you triangle 1 and triangle 2 belongs to R3. So this gives you, sorry, not R3, R2. So this will tell you R2 is transitive. Right. So once you finish, please let me know. Okay, let me just try to make a correction here. Please try to observe. There was a small mistake I carried on here. Otherwise, it will be a problematic one. So let me rectify this at this beginning. There is a small error I did. Error means about this element. Yes, this element. This element doesn't belong to R. Again, two cases will be there. Error means it was incomplete because of that I'm saying. Right? In this case, this B comma C has two options. I only said that it doesn't belong to R. This again has two options. What type of option? That this may exist outside R, right? Or it does not exist at all. right? This kind of situations will come. I'll take an example, then it will be better. Just you try to remember this one, right? So whenever you face this situation, if it is possible that it will exist outside, but not in R, then only your conclusion is trivially transitive, right? But if you face a situation where it doesn't exist at all, not in R, but never, nowhere, anywhere else, right? Then it will say not transitive. Remember it, right? I'll come to the example very, very clearly so that you will understand these things. Okay, so make a correction. This small correction you do because this is going to make a very huge sense when we go for the next problem we are going to discuss. So please see it, and once you corrected it, of course it may not be very clear right at this moment to you, but I'll take example then it will be clear. Once you finish, please inform. Okay, now I'll pick up the third example C. Example C was about less than or equal, that is about R3. R3 is transitive. R3 is transitive as if you start with A comma B belongs to R3, B comma C belongs to R3. That means A is less than or equal to B is less than or equal. Acha, together why I'm writing. Sorry, we will separate it at the beginning. Then it will be better. This and B less than or equal to C. So now you see if a simple number line you take, this A is less than B and B is less than C. So obviously A is less than C, less than or equal to C, right? This happens where in less than or equal to relation. So I can say that this is true. So if this is true, A comma C ordered pair will be also belonging to this. So it is transitive. We have already given the relation. Now we come to the very important part. That is the important one. Model 1 is important. It's a very important result. That is R4. So for that, let me try to take like this. For A, B, C belongs to set A. Suppose I am starting with this belong to R4 and B comma C belong to R4. So what does that mean? A is congruent to B mod of 3, then B is C congruent to modulo 3. What does that mean? 3 divides A minus B and 3 divides B minus C. Achha. If I get two numbers divisible by 3, obviously their sum is also divisible by 3. It is a normal divisor criteria. So what you will say? B and B will cut. So you got A minus C is divisible by 3. So does it imply that A is congruent to C modulo 3? Yes, definitely it will imply. So overall, what will be the result here? You got AB belonging to R3, B comma C belonging to R3 implies A comma C belonging to R3, and this happens for all these tribe, right, belonging to A. So it is therefore it is means R3. Sorry, R4 is transitive. This is transitive. I mark this as important because after some time, some point of time, remember it that we have to discuss some very important points about this one. Because of that, we know this is important. Now, only one small example is left out that I will be discussing. That is R5. R5 is transitive or it is not. R5 is not transitive. Remember it. Not transitive. As just I am considering like this, L1 comma L2 belongs to R5. L2 comma L3 belongs to R5. What will it imply? L1 perpendicular to L2 and then L2 perpendicular to L3. And these are happening in the same plane. Remember it. We are not talking about three-dimensional one. Had it been three-dimensional, we could have got these possibilities. But even it was not. It would have not been transitive because you would have got many examples which will not satisfy this. So from here, what will you get? It will imply what? It doesn't imply L1 perpendicular to L3, but it will imply L1 parallel to L3. That means L1, comma L3 does not belong to R5. Therefore, R is not transitive. That is already mentioned. Right? Please see that. I'll just take a break of. Yes. So I think this is clear to you. This is very clear to you. Now, before I take up any other examples on more type of relations, let us discuss. Then we'll go for the problems. Number 4. One more time is there. Equivalence relation. Equivalence relation. Now, what is equivalence relation? Actually, this is such a relation which is satisfying all the three types what we discussed. So, if we write any relation defined on a set A, which is reflexive, symmetric, and transitive as well, is called an equivalence relation. Equivalence relation. It is an equivalence relation. This is an equivalence relation. Right. So now, just if I look for example here, just you can pick from the previous one. R1. R1 is a relation of parallelism. And if you remember, it is satisfying all the three. So is equivalence relation. Right? Equivalence relation in that given set. Number, that is A. B, it was R2, triangle congruency, right? It is also equivalence relation. Number C, R3 is R3, it was about less than or equal. It is not equivalence because you can remember it is not symmetric. So it is not equivalence relation. Equivalence relation. D, R4 is, it is a good equivalence relation. Again, I am marking it. R4 is equivalence relation. Right? It was about the congruence model. Then this is E. R5 is not equivalence. Why? Because it is not reflexive and it is not transitive. It is only symmetric. So this is the example of equivalence relation. Of course, I need not discuss this separately. And one more type of relation is there, that is antisymmetric. Antisymmetric relation. What is antisymmetric relation? A relation R on A is called antisymmetric. Antisymmetric if A belongs to B, A comma B belongs to R, and B comma A both are belonging to this, implies that A equal to B. If this happens, if A equal to B, once A comma B and B comma A both are belonging, then we call it antisymmetric. I'll take an example. Right. See, let me discuss only those 5 relations. A. R1, is it antisymmetric? Is not antisymmetric. Why not antisymmetric? antisymmetric, as you may have L1, L2 belonging to R and L2, L1 belonging to R, but L1 is not equal to L2. Well, the lines are not same, so it is not antisymmetric. What about less than or equal to? It is antisymmetric. Why? Because if in case you get, I'm directly giving the region A less than or equal to B and B less than or equal to A, definitely it will imply A equal to B, because that is the only common option. Remember it, that is the only common option which you can have here, which you can have here, right? But at the same time, I just want to emphasize here also, because with that side, if I discuss about this, can this be antisymmetric? No, there is no question of discussing the antisymmetry of this, because once this happens, this cannot happen, right? So together it is not possible that they can held together, right? So it will not be, antisymmetricity cannot be discussed, right? Number C. C. No, here actually this is only C. Sorry, this is only C. B was about a triangle, that will be of course antisymmetric. No, not antisymmetric. Again, not antisymmetric, right? Because they will not be the same triangles. They will not be same triangle. Equality means here they are measuring as the same one. Remember it. Now number D. D means your this congruence model. So if I say that A is congruent to B mod 3 and also B is congruent to A mod 3, does it imply that A is equal to B? Here also it is not necessary, right? Because we are only talking about the divisions. So these numbers may not be equal. So it is also not antisymmetric, right? Last one is also not antisymmetric. So this is only the antisymmetric result we got. Okay. So have you understood? Now I'll be taking up examples.
Sir,
Hmm.
sir, the A less than B, B less than A,
Hmm.
that is that antisymmetric?
No, no, it is not antisymmetric, because we cannot discuss, both the conditions should held together, right? This should be together true,
Yes, sir.
and this cannot be together true on that
Yes,
numbers.
sir.
So it cannot be discussed only. It is not applicable.
Okay, sir.
We'll go to the next one. Now I'll be taking questions. I'll be taking questions. Some of the questions in the form of example. First two, three small examples we'll take, and then we'll discuss some of the important questions what I referred here. Question number one. Okay. Let R be a relation defined on the set of real number such that this R is A comma B, and if I get A less than B square related, right? Of course, A and B are taken from the real numbers, right? These were the things. Examine if R is number one, reflexive, number two, symmetric, number three, transitive, number four, equivalence. So these we have to examine now, whether this relation is reflexive, symmetric, or what, right? So now always whenever you need to check, if they would have said that so that, so it is having a general proof. But when they are asking you to examine, there may be possibility that that is not true. In that case, we may not give a general approach of proof, but we can give just counter example to disprove it. So now just let us try to see whether we can find some examples which are going to contradict the definitions. So we'll be doing it here. So just you see first here R A comma B belongs to R if A is less than or equal to B square. A and B are taken from the real number. We are now going to discuss about reflexivity. So for half belongs to a real number, half comma half does not belong to R, as half is not less than half square, because half will be more than half square. So therefore R is not reflexive. Actually, if you go on raising the power of a proper fraction, it will go on becoming smaller and smaller. By raising the power, you cannot make it bigger. Normally, power raising makes the quantity bigger if it is more than one. But if it is a fraction, proper fraction, raising the powers, it can be only made smaller and smaller. So that's the advantage you have taken here. So it is not transitive, reflexive. Symmetric is very obvious that it is not. So you can write for say 1 comma 2 belonging to the set of real number. 1 comma 2 belongs to relation R as 1 is less than or equal to 2 squares, but 2 comma 1 does not belong to R as 2 is not less than 1 square. Therefore R is not symmetric. Therefore R is not symmetric. Please see this. Once you finish it, I'll go to the next page, not in the blank space I'll write. Yes, so now I can go to the next page. Or you have sent the chat message. Let me see. Okay. So I'm going for the next page to discuss the remaining two conditions. Now, number 3 about the transitivity. But this is also not true. Right now, just let me see what exactly I have to show. This is a rough sketch I'm showing you. I have to show that this belongs to R. B comma C also belongs to R, but A comma C does not belong to R. That means A should be less than or equal to B square, B should be less than or equal to C square, but A should not be less than or equal to B square. That means A should be greater than B square. Sorry, C square. This is what you have to derive. In that way, you have to select the numbers. So once you can pick up the numbers in that way, so it will be good for you to identify. So how can we do this? You see, for example, let me make this true first. But at the same time, I have to keep in mind that this A should be bigger than C square, right? Okay. So say this is 4, right? This is 4. That means A has been considered as 4. And then B I want to consider as -3. And C I want to consider as 1. Now what you'll find, A will be less than or equal to B square because 4 is obviously less than or equal to 9. B will be less than or equal to C square, very obviously, because this is negative, and obviously every negative integer is less than every positive integer. But from here, can I say that 4 is less than 3? Because 4 means A, not less than 3. 1. This 1 is C square. So this is not true. So that is a contradiction. So we can write for only one example directly we are taking E equal to 4. Many more are there. I am taking only one. This, right? You can say the same step I am writing here. A less than or equal to B square. B less than or equal to C square. But A is not less than or equal to C square. That is A comma B belongs to R. B comma C belongs to R. But A comma C doesn't belong to R. Therefore, R is not transitive. So if this is not transitive, even one is not true, then also it is not equivalence. Here all the three are not true. So R is not equivalence relation. So done. Easy. And once you finish, please let me know. I'll go for the next question. Okay, here actually I will just try to write one question for you as a homework. That everything will remain same. The relation is this. You examine. For this, it is reflexive, symmetric, or transitive or not. Let me tell you the answer. It is also none. It will be also none of this. Neither reflexive, nor symmetric, nor transitive. Just try to show it. Right? It is having the same restrictions as I did for this question. Please test it at home, not right at this moment. Plus, please do it. Once you finish, let me know. Okay, thank you. I'm going for the next board. Now I'm going to take some questions. Question number 2, where I'll be getting some practical examples. Right, first let me discuss about those examples. What I told about the trivially symmetric, trivially transitive, and trivially non-transitive, right? So you consider a relation, right? Say A is a set of people in a particular, say, community, maybe the whole world, suppose, set of people, right? And then R, I am considering two element X and Y will be related if X is wife of Y and XY are picked from A, right? So now I have to discuss whether this relation is symmetric, transitive, or reflexive, right? One by one we'll go on discussing. You can do it easily yourself also, but still I'm discussing. Number one, not reflexive. More explanation is not needed only. It is a common problem. Not reflexive, as X cannot be wife of X, right? One person cannot be wife of itself, right? Okay, fine. Not symmetric as well, right? Not symmetric as well, as X is wife of Y. It will not imply that Y is wife of X, right? You think about the normal situations, right? Okay. Now we talk about the transitivity. X is wife of Y and Y is wife of Z. This should have been a certain point of transitivity, right? Now you will try to recall what exactly I wrote here. This thing is possible, suppose. Can this be possible? Possibility, you see. Whether in this relation it is possible or not, that I am not saying. Is this anywhere possible? नॉर्मल सेंस में क्या ये पॉसिबल है? ये नॉर्मल सेंस में कभी पॉसिबल हो ही नहीं सकता, राइट? दिस इज नॉट एट ऑल पॉसिबल. सो ये ऑर्डर पेयर कहीं आएगा नहीं दुनिया में. दिस ऑर्डर पेयर विल नेवर एग्जिस्ट. देयरफॉर, राइट, we cannot say about x is y of z, right? So I can say this is not transitive, right? It cannot exist anymore, so it is not transitive, right? Now, by the side, I want to take one more question. One more question. And then a question, जो target है, target remains the same. Question number 3. Say I want to consider A is the set of natural number. A is the set of natural number. And R is the relation where two natural number will be related if B is equal to A plus 5. And remember, A and B belongs to N, that is A. And A I restrict to a number less than 4. Right? So here will this be reflexive, symmetric, etc. So anyway, as this set is very small, let us try to write it in the roster form. If I give the input A as 1, this will be 6. Input 2, this will be 7. Input 3, this will be 8. Input 4 you cannot give because A should be less than 4. So this is what you get after giving the inputs. Okay. Now, one by one, we have to justify whether it is reflexive, symmetric, or transitive. Not reflexive, right? Very clearly, not reflexive. As you cannot say that 1, 1. In fact, 1, 1, 2, 2, 3, 3, none is belonging, right? So it is obviously not. I am just giving one counter example that 1, 1 is not belonging. Even 1, 1, one pair is not belonging. Then also it will not be reflexive because its domain will be what? That depends on the domain. Remember it. Domain of this relation is containing 1, 2, 3. So if these three elements are there, I must get 1, 1, 2, 2, 3, 3 belongs to R. Then only I could say that it is for reflexive. But here none such order pairs are there. Right? Not symmetric as well. Symmetric as well. Why? Simple. 1, 6 you can find in R, but 6, 1 you cannot find in R. Right? There is no confusion about this. I did not pick up this question for these two reasons. For the third one I picked up because third one is the most important part which you have to tackle. Now, it is trivially transitive. Why you see? Just you see. First, I'll do some rough work. It is not a part of the main part. Suppose you started with A, B belongs to R. Then you should start with B, C belongs to R. Right? Now, in the explanation I told you, there can be two possibilities of this. Either this will be in R or it will not be in R. Not be in R has two possibilities. Not be in R means it is not inside R, but outside it might exist. And it does not exist at all. Right? Here you see the previous question. It does not exist at all. Outside R or inside R is not question only. It does not exist anywhere. But in this case, in this particular case, if you start, I'll give the answer to you, but first I'm explaining it. If you start with the ordered pair here, next ordered pair should have been 6 comma 11, it does not belong to R. That is true. That is very true. But can you say from here that this never exists anywhere? You cannot say this 6 comma 11 can exist, may not be in R but somewhere else. So now on this basis, if I put forward your question that you give me an example which will show that it is not transitive, then you will have no example to prove or disprove this. Because if you wanted to prove that it is not transitive, you should have given me such example where a comma b will be there and b comma c will be there and a comma c will not be there in R. This is one way. Or you should have given me example that where a comma b is there and b comma c is never existing only. No. But you cannot give me that type of examples because immediately I'll question you, what about this? Because this exists, may not be enough. That means you do not have any concrete example to say that it is not transitive. So whenever you face this situation, your answer should be what? Trivially transitive. So how we can write the statement? I'm writing the statement for you, right? R is trivially transitive. Trivially transitive as in R there does not exist ordered pairs of the form A comma B belongs to R and B comma C belongs to R, and this implies A comma C belongs to R, or this doesn't imply A comma, or this doesn't imply A comma C belongs to R, right? You do not have such things, so we consider this as trivially transitive. See, my wordings are not very clear, so please try to rewrite the note immediately. Trivially transitive. So this relation is trivially transitive, whereas the previous one is not transitive. That's a very important concept, idea to relate. Once you finish, please tell me. I'll get into the next one. Okay. Now I'll go to the next question. Next question is very important. So it was what, question number 3. Okay, now I'll be taking question number 4. So this question number 4 is important question, very important. Question number 4, I mark this as important questions. This is very important question. So let us start it. Let us define a relation on Z, that is set of integers, such that R equal to A comma B, such that A congruent to B mod M. M is a natural number. A and B are taken from the Z. Is an equivalence relation. Is an equivalence relation. Please note down the question. I'm going to answer it. It's an important question. Okay, so now one by one we'll be doing. First, as a process, we'll write a relation. so that we make it formal. So we have this. Number one, we'll check about the reflexivity. For A belongs to not natural integers, what you say? A minus A is 0, which is divisible by m, any natural number. That means m divides A minus A. If this happens, I can say that A is congruent to A mod m. That means I can say A comma A is related. Therefore, R is reflexive. So one part we got. Number two, for A comma B belonging to Z, I have to start with A comma B belongs to R, and I have to finish with B comma A belongs to R. So I can say A minus B is divisible by M. That means M divides A minus B. So if M divides A minus B, M must also divide negative of that number. This tells you M divides B minus A. That means directly I'm writing now B is congruent to A mod M. That means B comma A belongs to R. So what will be your conclusion? Therefore, R is symmetric. Please note it down and let me you inform me. Okay, so this is symmetric. Now we are talking about the transitivity. Number three. For three elements A, B, C belonging to Z, we will start with A comma B belongs to R, B comma C belongs to R. That will imply us what? A is congruent to B mod M and B is congruent to C mod M. Very nice. This both will say that M divides A minus B and M divides B minus C. Now, if two integers are divisible by M, then obviously their sum is also divisible by that number. So now here you can see B and B will be cancelled and you can say this is divisible. So you can say that E is congruent to this mod of M. That means A comma C will belong to R. Therefore, R is transitive. Right? Therefore, R is equivalence relation. So whatever is told to you to prove, let ask you have proved it. Just finish it and then indicate. Because I'm going to drag this problem a little further. That you need to know. An important concept is waiting for us to be discussed. Okay. So now it's a second part I am writing. Actually, in the question there is nothing such second part mentioned, but I am telling you the second part. Suppose I want to define a symbol like this in a pair of brackets, third bracket, 0 I have written. So it is telling you set of all numbers related to 0. It is a 0. Now remember it, by the word number I am talking about the integers. Because it is referred to the previous this question only what I did. So all integers which are related to 0. What you can say? 0 is related to 0 because 0 minus 0 is divisible by M. Okay, now just a second. Here I have considered a divisor as M, so it is a general case. Let me make it little simplified by considering, say, M equal to say 4. M equal to 4. Because divisor is 4. So next number will be 4, 8, then 12, because 0 minus 12 is minus 12 divisor. That means all multiple of 4, like this. In fact, after going up to infinity, you realize that minus 4, minus 8, minus 12 should be also written. Right? So in fact, if you would like to write it in a better way, I can write it in this way. Minus 404. So indicating that I am including minus 4. Are you getting? Okay. So now, why I am doing, I'll come to that just after a few minutes. Suppose with 1 I would like to replace. So obviously this time as negative numbers will come, I have prepared myself. I'll write in the left side. 1 is related to 1 because 1 minus 1 is 0 and divisible by 4. Then what number? 5. Then what number? 9. Then what number? 13. Like this it will go on. Here it will be what? Minus 3. What it will be? Minus 7. Now did you find any peculiarity? We have found the peculiarity that each two numbers are differed by 4. Right? Right hand side numbers are obtained just by adding 4. Left hand side numbers are obtained by subtracting 4. Right? This is the idea. This is the idea I wanted to highlight. So here you try to see all these numbers are of the form 4 times some k. 4 times some k. That is multiple of 4. Here all the numbers, if you observe, 4 times some k plus 1. That means remainder is 1 when division by 4 is done. Now I can ask you a quick question. If I divide an integer by 4, how many possible remainders can be obtained? 0, 1, 2, and 3. Right? This already you got. So the first set is considered to the remainder 0. Second is considered for remainder 2. That means 2 more we are going to get. That means 2 more we are going to get. If I start with 2, I'll be getting 2, 6, 10, 14 like this way, and then minus 2, minus 6 like this way, right? And then I can go for 3. Then what will have 3, then 3 plus 4, 7, 7 plus 4, 11, 11 plus 4, 15, like this. And then it will be minus 1, minus 5 like this, right? And very well, you can now justify that if I consider all these 4 category of number, 4k, 4k plus 1, 4k plus 2, and 4k plus 3. Obviously, there will be nothing in common of this category of number because any number which is multiple of 4 cannot be of this type. Any number which is of this type cannot be of the other type. Meaning is that these 4 sets are such that they are mutually disjunct. If I try to find their common elements, what you will find? Nothing you will find. That means 5. And at the same time, you will observe because these are only the 4 types of numbers when you take the divisor. That means it includes all the set of integers, means all the numbers in the integers. That means if I take the union, then I am supposed to get the whole set and I will get it. So you can see how beautifully we have divided the set of integers z into 4 parts, where none of the parts are having anything in common with the others. And at the same time, all if you mix, you will get the complete set of z, and no integer is left out. And each of them are infinite set. That is also one of the other beauty, right? So these each of these named sets, right? These are the sets, right? This is one set you got. This is another. I just write it here. These are the sets you got. 4 sets you got. because you have considered the divisor as 4. So each of these 4 sets are said to be equivalence class. Right? Equivalence class defined determined by R, not real number versus relations. Whatever is the relation we did. And this is happening because you have considered the divisor as 4. Had your division been 10, you would have got how many equivalence classes? 10 equivalence classes. And each of them would have been of infinite size. Their union would have been the complete Z, and it would have given you disjoint sets. Am I clear to you so far? Okay. Now you see, why did I stop at 3? What would happen if 4 I start with? Acha. If I start with 4, then there will be repetition, because you know that already only 4 different types of numbers will be there. So if I start with 4, 4 is a number which is divisible by 4, that means multiple of 4. So now if you find the set of numbers which are related to 4 is nothing but the set which is obtained by 0. And this is happening because you can see when you try to work out 0, this 4 is visible here. So all the integers which are related to 4, that will contain 0. Now my conclusion is that if any equivalence class you get here, then it is totally useless to take the equivalence classes of any of the elements belonging to this sets, because it will define the same equivalence class. Right? So from here we can get some properties like this. Right? If A is related to B, then equivalence class of A and equivalence class of B are same. It is not necessary that A and B should be equal, right? It is not at all necessary. But if they are related, whatever equivalence classes they will define, they will be same. And in the reverse direction also, if equivalence classes are same, then elements are related to each other. So this is one of the very important part we get. And remember, every equivalence relation will give rise to such equivalence classes which are disjoint and exhaustive. Exhaustive meaning is that their union will give you the complete set A. Right? So if you have any queries or question, you can ask me.
No, sir.
It is okay? Okay.
Yes, sir.
So now I'll be going for one more question. Question number 5. Question number 5. Let R equals A minus B such that mod of A minus B is divisible by 4, and A comma B I want to take from Z. Right? Examine if R is equivalence. क्या R equivalence relation है, एग्जामिन करना है. Right? Number 1, you write for any A belongs to Z, what is A minus A mod? Obviously 0, which is divisible by 4. Therefore, I can say that any A comma A will belong to R. Therefore, R is reflexive. It's done. Number two, for any a comma b belongs to Z, I start with a comma b belongs to R. That will indicate that a minus b is a minus b means mod of a minus b is divisible by 4. Okay, if mod of a minus b is divisible by 4, obviously mod of minus of that number is also divisible by 4. There is no doubt about that because results will be same for both. So inside it will be what? B minus a is divisible by 4. That means b comma a belongs to R. Therefore, R is symmetric. Okay, once you finish, please inform me. The last part is little important. Okay, so I'll come for the transitivity part. Number three, we will try to solve the transitivity. Right. So for ABC belonging to Z, we have to start with what? A comma B belongs to R and B comma C belongs to R. And we have to conclude A comma C belongs to R. Then it will be transitive. Anyway, let us not be coming to the conclusion immediately. So I can write this is divisible by 4, and then my mod of B minus C is also divisible by 4. Okay, so here you see directly addition or subtraction. If I do, it will not give us any result. So what we'll do, I can in that case say that if mod of A minus B is divisible by 4, A minus B will be always of the form 4 times some m. Plus or minus I have written because maybe A smaller, right? So B minus C is also plus or minus 4 times of some m, where m and n are integers. Right. So now you can say that their addition can be possible. Now do the addition. If I do the addition, what will I get? This one. B and B will get cut. So A minus B will be equal to plus or minus 4 times m plus n. Is m plus n an integer? Yes. So from here, can I say that this is divisible by 4? Yes, I can say. Therefore, A comma C belongs to R. Therefore, R is transitive. Hence, R is equivalence relation. Because you can see it is transitive, reflexive, and symmetric all the three. Right? Right? So now can you find a quick relation between this question and the question we did previously? They are actually the same. Representations are different. Right? When I considered m equal to 4 in the previous question, whatever we did is very much same here also. But because of the presence of the modulus, we'll have to attempt in a different way in the representation. Otherwise, questions are same. So here also I can ask you that you find say 4. That means this symbol itself will indicate that I am talking about finding what equivalence class of 4. So here what will be there? All those numbers whose difference is divisible by 4. Rather you can say all multiple of 4. Positive, negative, whatever it is. Right? So likewise you can find the equivalence classes. So Swarna, today I'll leave it here. So you first see, if you have any question, any queries to ask, you can ask me.
No, sir.
Okay. So I'll be leaving you today here. I already dragged half an hour more. I don't know whether you are like comfortable or not. Anyway, so see you next day. So today I'm going to sign off. Bye.